Okay. Hello, Bivan. um, I I made this thing on Desmos, and so I wanted to show it to you. But then I figured I'll go ahead and tell you the full story of how I came across making this thing. Also, because you make like videos like this. Um, Anyways, okay. So I've been wrong starting point. So I've been working through this book. It's called the Complex Book. Actually, let me just go to the beginning. Um, I don't even know where I found it, but it's just like complex numbers. And so I was like, sure, I want to know Riemann stuff. I want to know about the Riemann. I haven't gotten there yet. But I was working on 1.3, section 1.3, and then I was working on problem 23. So I mean, I've been kind of slow at these problems. Like the generalized triangle inequality took me, I don't know, took me longer than I expected. And then the next problem was this one. So it's like let m1, m2 be three positive real numbers, and z1, z2, z3 are complex numbers, each of modulus less than or equal to 1, and then use this generalized inequality to prove this. So I was looking at this and I like recognized kind of what's going on here, but also it just seemed like numbers multiplied to each other and it didn't really make a lot of sense. Especially like I was quite stuck here and I was trying different things. Like for example, since I knew m1 times z1 plus m2, like since I knew that if I had a fraction with this on top and bottom in the numerator and the denominator, it would be greater than or equal to 1, then maybe I could get this to show like if it's less than that fraction somehow. But I was getting stuck and I didn't know. Oh, it also says give a physical interpretation of the inequality. And so I was kind of lost on that. I was like, I have no idea. This book is written kind of assuming you have a background in engineering, or physics, or even some higher level math like calculus. So it's definitely not a beginner book, and sometimes I found myself wondering, like here you'll see a piston problem that they do. Like I think I can figure it out, but like I haven't done physics like that in a while. So I was like, okay, this is probably like some higher level physics I'm missing. I just need to do the proof. But I couldn't figure it out. So I went to my trusty friend ChatGPT and I told it what I was thinking, and I told it act like a classmate, to explain or like maybe give me some ideas. Except it didn't act like a classmate, in my opinion, and just gave me a straight answer. So I was like, okay, that's not what I wanted you to do. But I could see like, okay, somehow it did stuff, and I was on the right track, um, because this is the fraction that I got that equals 1. So I was like, okay, maybe kind of on the right track, but I still didn't get it. And so I asked it to be more conversational, like explain a little bit more what it was thinking. And then it gave me this. A useful reframe you were edging towards was like this. Blah, blah, blah. Like it just says stuff like intuitively convex combos and all that. I have no idea what it's talking about when it's saying convex combos. And then sit with that picture. Weighted average points inside this unit disk stay inside the unit disk. So I feel like you so some like people that are quick with this, I might say you're one of them. You could have seen like z1, z2, z3 that have modulus less than or equal to 1 and immediately thought like, oh, okay, so these are complex numbers within a unit disk. That thinking didn't happen for me, but when ChatGPT pointed it out, oops, um, then that's when I was like, wait, where is that coming from? How is this coming from a unit disk? So before I show you the Desmos last thing, I just re-looked at the problems from before, and I feel a little bit sheepish because I think a lot of people could look at that problem and, like me, not know that this is a center of mass of 3 points in a system, essentially, right? It had already talked about that in the book, and it had gone over an example. And I remember thinking to myself, like, oh, to find the center of mass, you just find the center of mass in each dimension, which made sense to me. But somehow I just didn't connect that to, okay, so for this problem, you're dealing with masses that lie within a certain radius. So these masses lie within a unit disk. And then you have to prove it. I guess it doesn't change it, but just the fact that it didn't come up as an image for me made me think, so I got to make an image out of it. So I went ahead and, I pulled up Desmos and I started with like stuff like this, like m+1, m1 plus m2, m plus m3 is equal to something. And then I tried to make stuff from z, and originally I was just using real numbers here. But as you can see now, these z's are corresponding to x1 and y1. But originally, like, I was just trying this stuff and seeing how to come up with the visual. But Desmos is pretty powerful. So once I remember, like, okay, well, every complex number I can just write as like an x and y component, then I can put it into Desmos, even though it doesn't work with imaginary. Well, actually, I'm not sure if it doesn't work with imaginary. I'm also just going because this guy makes me think it does work with imaginary. Like, why does it have these kind of coordinates? Possibly. But I don't know how to do that on Desmos. In any case, or like complex numbers. In any case, so once I remember this, okay, I can break this up, and then I'll just have to work with each as its own dimension type thing. So then I guess I'll just start going over what I have here. So firstly, I have the center of mass of this system is A and B. And you can see that from the original problem info. The way I do it, like I explained, to find the center of mass, you just find one coordinate of the, like one dimension of the center of mass, and then you find another dimension of the center of mass. So I found that here's the x dimension of center of mass, and then the y dimension of it. Great, so that gives us the points A and B. Also, as you can see, I have M1, M2, M3. These are three different weights, and I could change them around, but all of a sudden you see when I change them around, this dot starts moving around. Because this dot is affected, since it's the center of mass, it's affected by a change in mass over here. So I thought that was pretty cool. Let me see what happens. Okay, so if I highlight that one, nothing has really happened, nothing has really changed. Yeah, because there wasn't really any visuals coming from there, but except for the AB. So that one's already in there. Now, I add in the next one. Boom. So what is this complex points? These complex points are the actual location of, here you see all these Z1, Z2, Z3 were based on X1, X1, Y1, X2, etc. And here are the X1, Y1, X2, Y2, X3, Y3. And these were all located at different points in space. So essentially these are our complex points just being represented as x, y coordinates. And as you can see, they're in a particular location such that our, with these weights, the center of mass is located at 0, 0. Which I had a little bit fun figuring out how to do, so that it wasn't just like they're all three in a line or stuff like that. This makes it look cool, like kind of unbalanced and stuff like that, which makes it cool. Great. So let's get to the unit disk too. The whole point about this is that like these are all within a distance of 1. So here you can see like the different distance for the different points. Ooh, maybe I should add a label Z1 to like this point, a label Z2 to whichever one Z2 is. Yeah. Okay, cool. I'll think about doing that. And then resaving it with that. But so here are the three different points, and the thing is they're all supposed to lie within a unit disk, which you can see now. Oh, I wonder too, I'm gonna do this really quick. Sorry, I feel like I'm just wasting time here. But I'm gonna, since it's a unit disk, we don't just want a circle, let's go ahead and make this inequality, right? Let's make it lie within here, and then let's change the opacity on that though, so that this is like 0.2 maybe. So it's a little gray, but like not too gray. I wonder 0.1. 0.1, 3, 3, 3, 3, 3. Okay. Okay, great. So now it does look like they lie on a unit disk. So let's go ahead and get, well, actually, on these points, you can see that they have this little thing here, which means that I can actually grab them and yank them about. So I can move them around as I see fit. And so one thing I had to do with that is like, okay, well, part of the thing though is that like you can't just move them all around, right, these unit points, these complex points are supposed to lie only within the disk. So I went ahead and like at first I just had them going all over the place, but now you can see it kind of hiccups a little bit when I go into certain spots of the circle. And the reason that is, I'll go ahead and show you. And I guess like watching your videos just like made me realize, I mean, it's been a while since I watched them, but still like there's so many things like that Desmos can do. So it actually can take an expression in here. So for this first point, let me figure out, oh, green is the first point. So for this first point, the y values aren't allowed to go beyond what you see on screen right here. So the square root of 1 minus x1 squared, etc. So that's why you have the little hiccup. Well, so that's why it doesn't go beyond it, because it's bounded by it. But if we have, I realized there was like a little hiccup there, and you could actually take the point further if you didn't limit the x. And I guess you can try to figure out why. I didn't fully think about it, but at this point, yeah, it would just let me go out before if I didn't have anything on the x. Like I could delete this and delete this over here. I'm not sure why, but like it'll let x go beyond there, but obviously that's not what you want, because then you start getting this error over here, and also you're not like following the rules of the problem, like the visualization. So I first tried to put the opposite, which was negative square root of 1 minus y2 squared. Oh, I guess that does work. Wait, what? Square root of 1 minus y. Oh, I put y2, that's why. Because, so that's a whole different variable, it has no issue with it. But if I put y1, which is bounded by x1 itself, then it starts giving me a hard time and actually doesn't render the problem. But, so I'll go ahead and delete this. It won't render it for whatever reason. Right here it's saying, I don't know why it's in Spanish either. Oh my god, I don't know how long this is. Okay, I promise I'm almost done. Anyway, so this one works well enough, except it has that little loop right there that gets out, and sometimes it glitches out. So all I did was then just, okay, well, let's fix this one. Let's fix it by putting limits on it, and then it mostly works the way you kind of want it to, except now it has a little hiccup there because Desmos detects that as like a, oh, that's an important point, so I'm just going to assume if your mouse is close to there, then I'm going to get to that point. Okay, great. So cool. Now you can kind of see that the whole point here, sorry, of the visual, back on track. The whole point of the visual, you can now see, let's go back to the problem really quick and see what we're trying to prove. You were trying to prove that if you have 3 masses, you see they said positive real numbers, not masses. So that's why I didn't even visualize like masses. And 3 positions for those masses, you want to use a generalized triangle inequality to show that this is going to be less than 1. And again, this is the center of mass. So now, if you think of the center of mass, think to yourself like, oh, is there any way that I can put these 3 points somewhere on the circle so that the black center of mass is outside of the circle? That's essentially, like, maybe that would be like a proof by contradiction. Is like, or you know what I'm saying? Like, this inequality is saying like the center of mass is always going to be within the circle. And once you see that, once you know that, then you're just like, duh, like how the heck am I going to get, if this is like, in one way to think about it, the middle of the 3 points, then it's never going to be outside of the circle because the 3 points can't be outside of the circle. So I think it's like a cool way to see that, just like, duh, a duh way. Yeah, so but the other thing that's kind of missing here was like these weren't just points, right? They had a different mass to them, and you can see they have different mass right there. So the last thing I want to do to the visualization is just make them look like kind of like points how they are, so like kind of masses, which the problem didn't mention but ends up being really important to how to think of it. So now you can see like these are circles of certain radius, and if I change the radius, then so too does the, sorry, like if I change the mass, so does the radius of the circle, kind of giving some impression of like, oh yes, the size of the circle is tied to its mass. Um, and so these aren't just random points on a plane, but they're actually like things that have mass. And as you can see, as I change the mass, as the circle gets bigger and presumably has more mass visually, it's actually, yes, it does have more mass visually because it's affecting the center of mass of the system. And then you can just, play around with the three different masses and see what happens. You can turn one to 0 and then see that when you move that mass around, it no longer affects the center of mass because the mass of it is 0, so it's not having an impact regardless of where it is. But then maybe you do increase the mass by a little bit. Oh, my computer is glitching now. Hardcore. I hope it's recording. Okay. Maybe I'll just stop talking now. I thought this was fun. I'm going to go ahead and reload it just to have it in the standard form that I have it. And the only thing I'm going to change here, so this is how it would like pull up to a student or something. It's going to make it less than or equal to. And then I do want that opacity to be 0.1333. Anyways, yeah, so this is what gets pulled up. Now I'm going to save it like this. This is what gets pulled up when a student sees it. I don't know. I had a lot of fun with this. Here are the locations of the things, which, like, yeah, it wasn't too hard to figure out a way to make them, make the center of mass 0. Oh, no, it's not 0 right now. What happened? One of the points is wrong. This one should be 0. U should be 0. Oh, I guess I moved it a little bit. Let's make sure it stays with that. Okay. But yeah, I don't know. Let me know what you think in the comments, I guess. Or text me. Okay. Talk to you later. Bye.